Okay, so in this video, we're going to take a brief detour away from what we've been previously talking about and discuss learning objective functions. And I figured this was important because we've been talking a lot about optimizing certain objective functions like the log likelihood that we would maximize or the negative log likelihood that we would minimize. And we went over different methods for optimizing these objectives. But I think it would be useful to think about these things in a more general context. So the outline of the video will be that we're going to talk briefly about how optimization plays a big role in machine learning. And then I will attempt to categorize optimization problems into different types. So I will consider unconstrained and constrained optimization. I will talk about using Lagrange multipliers for constrained optimization. And I'll talk about convex objectives, non-convex objectives, and discrete optimization problems. And most of this discussion will be at a fairly high level, but hopefully I can make some connections that will be useful. So in machine learning, a lot of machine learning methods, not all of them, but a lot of them can be posed as essentially just an optimization. So usually we have something like what we've seen with the logistic regression, negative log likelihood or regularized negative log likelihood, where we take a model and we parameterize it, and then we run some optimization, run a search over a parameter space for something that gives us the smallest possible objective value. So sometimes we will refer to this as a hypothesis space, although it's more like there's a mapping from the parameter space to the hypothesis space. And in this particular objective function, we have something that is a regularizer, and then we have something that's a loss. And this together forms the full objective function. At a high level, you can think of this as just us designing, as machine learning model designers, we design what is considered a good model. We say, well, we want the model to be simple, so we add a regularizer, and we want the model to predict the training data well, and that's the loss function. We add them up and we decide on some weighting between the two, and then we essentially abstract away the problem of trying to find a good model, and we just say, let's just let some optimization algorithm do it. Of course, in practice, we often have a lot of control over the optimization algorithm, and sometimes we have to build it ourselves. But from a design perspective, it makes sense to abstract it away and think of this as just, this is a black box argument operation, and we're just designing this objective function. Of course, the reality is, like I said, this is not truly a black box. A lot of times we have to implement the optimization algorithm, or even if we are using someone else's optimization algorithm that they've written, or some other optimization software, we have to understand the properties of different optimization algorithms, the types of problems that they can solve, and the types of behavior we should expect given the type of problem we give these algorithms. So that's somewhat the goal of this video. So I'll talk about different types of optimization problems. Like I said, we'll talk about whether they're constrained. I'll briefly mention Lagrange multipliers for constrained optimization, which will explain how we can think of constrained optimization as unconstrained optimization. And then we'll talk about convex objectives, non-convex, and discrete objectives. So in unconstrained optimization, which is basically the easiest kind of optimization to think about, you might just look for a solution. You might be looking for a solution that is somewhere on the real number line in one dimension. So in multi-dimensions, it's on the real number vector space, but in one dimension, it's just a real number, any real number. And our task may be to find the minimum of some function. So maybe we're looking for this point right here, which is the minimum. So in unconstrained optimization, the only thing that controls where we end up is the function itself. The function may be curvy in some parts, and that makes it so that it prefers, or it will give you a lower score or better score near, say, 0 or some number. It doesn't really matter. But it's completely determined by the objective function. Right, and you can plug in values for any input from minus infinity to plus infinity. Well, not exactly, but from a conceptual perspective, that's the case. But in real computers, then there's a limit to the size of floating point numbers you can compute with accurately. So in contrast, constrained optimization puts constraints on the possible solutions. So for example, maybe we say, okay, let's minimize this blue curve function, but we're only allowed to consider values, input values between minus 10 and 100. And these are totally arbitrary numbers I made up. So now the original solution, which I've now grayed out on the screen, is no longer a valid solution, right? It's greater than 100, so we can't use it anymore. So the actual, right, the solution in the picture now would be this point here on the right edge of the allowed space. So if we assume that we have a technique to do unconstrained optimization, for example, gradient descent or its variants that we talked about in the other video about logistic regression, then there is a strategy for taking this constrained optimization and turning it into essentially an unconstrained optimization that those methods would work on. And it's something called a penalty function method. So we might do something like create these penalty functions that go from 0 and curve up suddenly asymptotically toward infinity as we reach the boundaries of our constrained space. And we add that to the original objective function, and we get something that looks like this, where maybe the optimum of the red function is now someplace over there. And of course, this is not good because what we wanted is to be even closer to the boundary, so you might want to make that penalty function more sharp so it's not as curvy. But ultimately, it's the same idea, and methods that use this idea will do something like iteratively make that penalty function or that barrier function more and more peaked, so it's closer and closer to something like a step function. And note that this is an unconstrained optimization, but sort of in a silly way, because what it means by it being unconstrained is that any valid number or any real number is still a valid input, but any real numbers that are outside the constrained space have an objective value of infinity. And with this, the curved barrier function essentially says that as you get closer and closer to that boundary, you get closer and closer to infinity. So another approach for handling constrained optimization is to use something called a Lagrange multiplier or Lagrange multipliers. And what the idea behind a Lagrange multiplier is it's also a form of penalty function, but it's a little bit different in that you start with the original constrained optimization, so something like what I wrote on the screen here. So you have a minimization over the variable x of some function f, subject to some constraint, and the constraint is written as another function g, right? So g of x has to be 0. So in the picture I've drawn here, we can just say that g of x is equal to the indicator of whether x is in the interval minus 10, 100. So that is only 0 in the allowed green space, and it's non-zero or 1 in this case whenever you're in the disallowed space. So here's how we change this into a Lagrange multiplier expression. So we change it into, we're still doing a minimization over the variable x, but now we also have a maximization over some other variable alpha, and this alpha is the Lagrange multiplier. And alpha multiplies the constraint function g. So it's so we have f of x and we have plus alpha times g of x. So if we think about this objective function, what it looks like is it's a game, right? Where we're the minimizing player and we're trying to minimize the function as much as possible. But then there's this other maximizing player, this bad guy who's messing around with the alpha value. And the bad guy basically says, I'm going to make you have to pay as much as I can while we're trying to pay as little as we can, or pay as little penalty as possible. And one way we can win against this bad guy is to pick a point within the allowed space, right? So if we pick a point within the allowed space, here or there or there or there, then the g of x function is 0, and the bad guy can't do anything, right? All they can do is multiply 0 by alpha, and nothing happens. So we get to minimize f of x, we're happy, and we have no, the bad guy has no power over us. Okay, but now if we violate the constraint, if we use this point or this point, then what we get is a non-zero constraint function g of x, and the bad guy, our adversary, can set alpha to plus infinity or minus infinity and make our objective value as bad as it can possibly be if we're interested in minimizing it. So this expression here that we're both minning and maxing is something called the Lagrangian. And it's obviously of a different form than the type of objectives we've been looking at, because now there's two players in the game. It's not just one person trying to minimize, but it's a min and a max. And that is a form of optimization problem called a Saddlepoint Optimization. And usually with Saddlepoint objective functions, we like the property that we like to see that if you fix one of the variables, whether it's the variable being maximized over or the variable being minimized over, then the adversary's problem is well behaved. So here's an example of one of these problems, and you can see that you can probably see where the the name Saddlepoint comes from. It kind of looks like a saddle, but the idea is that our goal is to find a point where neither player can improve their performance, can either minimize or maximize the function any better given the current value of the other player's variable, right? So we're looking for a point where, as the x player, there's an alpha value for which we can't improve the objective function by minimizing it. We can't minimize it anymore, and as the max player can't move alpha around to make it any bigger. But I wouldn't worry too much about Saddlepoint optimizations for now. Let's just say that there are ways to make them well behaved in a way that allows us to take advantage of the Lagrange multiplier idea and compute constrained optimization. In fact, we're going to do that when we study support vector machines. So moving back up a level, let's think about what makes an objective function nice. And one thing that makes an objective function nice is convexity. So convexity is defined as, in a very loose sense, a function that is only curvy in one direction. Now, of course, that's very loose and very colloquial, but formally, what's defined as is that it's if you take any 2 points on a function and you draw a line between those 2 points, that the actual function value is going to always be below that line. So even though I've drawn this in one dimension or for a one-dimensional function, this same idea extends to multi-dimensional functions. And this is the way that it's defined in notation. So the function of alpha times x1 plus 1 minus alpha times x2 is less than alpha times that function at x1 and 1 minus alpha times that function at x2. And what is this talking about? Well, so first off, let's give some more definitions for the domains of these values. Alpha is going to have to be a number between 0 and 1, so you can think of it as a proportion. And x1 and x2 are points in the real vector space. So what this expression is saying is that if we evaluate the function at a mixture of 2 points, right, where we're mixing it, at the proportion of alpha and 1 minus alpha, that always has to be lower or equal to the average or the weighted average of the function at the 2 endpoints. So there's a couple examples of convex functions we've already seen. So this is the logistic regression negative log likelihood. Actually, what we're seeing in this picture I plotted is probably more the regularization. So here I can spin it around a little bit so you can see what this should look like if you've seen visualized these things before, is it actually should look a lot like a quadratic function. But there's a little bit of a skew, a shape that's created by the logistic regression likelihood. But once you get far away from zero, the quadratic really takes over. And you probably have seen this before, how quickly a quadratic function grows as you increase the quantity being squared. So on the right, we have the Bernoulli negative log likelihood, which is another example of a convex function, but it's kind of a funny one because unlike the logistic regression parameters, which are in some exponent, right? That's a w that multiplied by the data and are exponentiated and then normalized. The Bernoulli parameter space is is actually just the probability, and the only parameters that make sense are numbers between 0 and 1. Right, because we don't want any probabilities that are greater than 1, or we don't want negative probabilities. So in some sense, the Bernoulli objective function, should be constrained because any numbers outside 0 and 1 don't make sense. But it turns out that because of the form of the negative log likelihood, the score actually approaches infinity as you approach 1 or 0. And the reason for that is because there's going to be a log of 0 in either the probability of 0 or probability of 1. But then beyond that, technically the function is undefined, but we could just make something up and say, well, look, it's going to be infinity as you approach 1 or 0, and let's just say, for the sake of making this nice and easy to work with, it's also infinity everywhere outside of 1 and 0. So everything greater than 1 is also going to give us a score of infinity. Everything less than 0 is going to give us a score of infinity. And then what we have is an unconstrained optimization over the entire real number line, which only is non-infinity or non-infinite within the 0-1 interval. So there's a lot of nice things that happen when we have these convex functions. One of them, the nice things, is that we have guarantees about finding the true minimum if we run one of these gradient optimization methods. But one of the things that you lose is that there's a lot of really interesting models out there that have non-convex objectives. So when you have non-convex optimization, you have kind of a funny warped shape objective that has some curves that are essentially upside down bowls, or there's a mixture of right side up and upside down bowls, but we still want to minimize this. And an example of this is what I'm plotting here is a sort of weird looking 2-layered neural network. So this is kind of like the multi-layered perceptrons we looked at in the last video, but there's only 2 variables. So there's the input variable and the output layer weight. So the input layer weight and the output layer weight. So it's probably not the most useful, practical neural network you might look at, but it gives you an idea of what strange surfaces we can create with these multi-layered logistic functions. So if we wanted to optimize this thing, then we can take the local optimization approach and basically do gradient descent the same way we would have with a convex function and just hope that it works. And what can happen is you might have a wavy, curvy surface that you're trying to minimize, and you start with some initial point here and you move and things are going well, right? You're sliding down that gradient, and this is exactly what we want to do. But then you might find yourself stuck over there. And the problem with gradient descent is when you look at the slope of this curve there, if you zoom in a lot, the slope of the curve at that point is basically 0, or is 0 essentially. And what that means is when we run, if we use gradient descent, we have no way to tell that this is not the true optimum, right? We can't tell. So what we end up with is that we're just going to stop here, and we have what's called a local optimum, or since we're minimizing here, a local minimum. Now, in practice, a lot of times these local minima are good. They're good solutions that we're happy with. But the fact that we know that it might not be the true minimum is concerning. So another approach for handling these non-convex minimization problems is to use a bounding method. So you might say something like, you start with some initial point here, and you create a convex function that bounds the curvy true function we're trying to minimize, and then you minimize that bounding function. And you might end up over here, and just in this cartoon, we would do this 2 times, and we end up with the true optimum. Of course, I only drew this cartoon this way just to show that different things can happen. If you have a different step size for your gradient descent, you may also end up in the true optimum in this picture. But in both cases, you may end up in a local optimum as well. So it's not that one is better than the other. These are just different strategies for handling the non-convexity. Okay, so the last type of optimization problem I wanted to talk about is discrete optimization. And we've done some of this already. So we talked about feature selection and decision tree learning. And it's often the case that when we want to do discrete optimization, we can pretty easily create objective functions that are intractable to exactly optimize. People with a computer science background will recognize that discrete optimization is at the core of a lot of computer science algorithms, and a lot of computer science problems in computer science are known to be intractable problems, and they are discrete. So one strategy we take a lot in machine learning is to relax the problem into a continuous form, and then essentially either hope that the solution to the continuous optimization is good enough and close enough to the true discrete solution, or we analyze it and show that it's boundedly close to the true discrete solution, or we just run it and show that it's doing something reasonably intelligent. So we won't spend too much time with discrete optimization in this course. We've already done it with decision tree optimization, where we took a greedy approach to building that decision tree. But if we look at the objective function that we're minimizing, it's not so clear that the greedy approach gets us necessarily the best solution. Okay, so popping all the way up, let's try to look at the different attributes of objective functions that I've been talking about in this video, and try to categorize some machine learning techniques that we know about, that we've studied and that we've previewed for future course lectures. So one of the categories we're interested in is whether things are convex or non-convex. And in the convex space, some optimizations are constrained and some are unconstrained. So for constrained optimization, I already mentioned in the video that support vector machines can be viewed as constrained optimization. Logistic regression, we saw it's unconstrained, right? We allow weights to be in the full real vector space. Perceptron similarly can take on any real vector. Naive Bayes is kind of in between constrained and unconstrained, depending on how you represent the parameter space. So we talked about how the multinomial probabilities have to sum to 1, so it's in some sense, it is constrained. And similarly, the Bernoulli probabilities have to be in between 0 and 1, but we could also take the perspective that these are unconstrained objectives with infinite scores outside the valid values. And also support vector machines show up again as unconstrained methods, because you can think of the optimization in multiple ways. You can think of it as a hard constrained search or a soft constrained search, in which case it's unconstrained. And we'll get into that when we get to that. That's the support vector machine material. So for non-convex objectives, we saw the multi-layered perceptron in the last video. I didn't go over how you actually optimize the thing, but we've seen that even just with one hidden unit, an input unit and a hidden unit, and then the output, we already have a non-convex objective. Another thing we'll look at for non-convex optimization is expectation maximization, specifically in the context of clustering. So that's a situation where we will be fitting probability distributions, a mixture of probability distributions, to data, and that creates a non-convex objective. And then discrete optimization is another category, and we talked about decision tree learning as one of those possible instances of discrete optimization. Okay, so finally, I'll just mention that the Saddlepoint type optimizations is another class, and yet again, support vector machines kind of shows up there, although it's it only becomes a saddle point mostly in the perspective that you'd use Lagrangian techniques to handle the constraints. So that's why it's sort of a constrained optimization and a saddle point and an unconstrained optimization. And then expectation maximization also will have a saddle point interpretation, which we'll get into. It's not too important in getting it to work, but it's an interesting connection to note. So overall, this should give you a very high-level view of how optimization fits in with machine learning. And once we get in the next video, we'll get back into details about one particular algorithm, and there we'll have more context to discuss the search for good parameters as optimization problems.